is the Black happening in the Broad First Nation area and in this community. The other thing, later you will see, in fact, we started this work a long time ago by looking at this emerging in the future, the threat of mosquito borne or vector-borne disease to this community in the north. The second part mainly is about the training program. So this part, the story is still under developing. So that's why we want to work with the community. Also, we work with the Canadian Society of Industrial and Applied Maths to develop specific training program to involve more people. Also to have this training program happening in the indigenous community. This part, in fact, full of challenges. We are working on this. Original plan was the summer training program. Obviously, we will need to postpone this to some later time in fall. Before the end, because after the meeting, we are going to revise and submit the final proposal to answer for approval. So this is the update. We will have time at the end for some discussion. Christian?
Good morning. Can you hear me?
Yeah. Good morning. Sharika, are you able to make Christian the co-host so she can hear her screen?
Leave that.
Huh?
You want to log off your sharing? Some of that there, stop sharing.
Yeah, make her yeah. Go ghost.
Can you share that screen now?
I'll try now.
Oh,
Yeah, it's gonna work. 1 second.
Okay, yeah, this is if you mind. Perfect. Yeah.
Sorry, I'm just gonna. Can you see?
Yeah.
Okay, perfect. I'm certainly not someone who's tech savvy. So just a little bit about the title. So living with black mold. Unfortunately, some of the communities that do exist in and across Canada have been faced with some instances of black mold, and I'll share a picture a little bit later on just to give you a glimpse into what that looks like. As for myself, just a quick introduction. We typically do introduce ourselves in the language, so I'll introduce myself and kind of give you a little bit of a background. So, Wache Miswe Kichitawi Siwen Mikaso Esqueo Nijnakazin. So my spirit name is Sacred Eagle Woman. I am Bear Clan. My First Nation where I'm registered is Chapleau Cree First Nation. So we're about 2 hours from Timmins, Ontario, where I currently live. And I am a resident of Timmins. I've been on council, so this is my second term as an elected official. I ran in 2018 and got in, and then served the last part of my term as mayor because our mayor stepped up as was elected as our MPP for the Timmins region. So I stepped in, completed the rest of the term as mayor, and then ran again in 2022. So second time elected official, and just really proud to be here today. I think it's a very important topic, and it's kind of interesting how things came to be. We're very relational as Indigenous people, and I think just having conversations with the group about the work has been really refreshing because Waiping has been really excited. Sometimes it's interesting to see the interactions we have with one another as we're carrying out some of the meetings. So just a little bit about myself. Um, so obviously, what is black mold? So I'm pretty sure that people on the call would most likely know what that is. So it's a common word for any fungus that grows on food or damp materials. Can be black, white, or almost any color. Looks like a stain or smudge, and it may smell musty. So in order to grow, mold needs moisture and a material it can live on. It then releases spores into the air, which are small enough that people can actually breathe them in, and breathing in large amounts of these spores and byproducts they can produce negatively on your health. So a common place for them to grow indoors are on windowsills, fabrics, carpets, walls, and kitchens, bathroom, laundry areas. And then so the relationship with between mold and damp conditions, there is a relationship between indoor mold, damp conditions, and increased. So some of the health related things are eye, nose, and throat irritation, coughing and phlegm buildup, wheezing and shortness of breath, symptoms of asthma, allergic reactions. So covering the issue of mold remediation is big, and the problems stemming from it are diverse. As such, we need the people from First Nation communities to be provided with opportunities to get training and skills to combat these issues. So instruction in building systems technology and building better practices that stand up better to the environment and great construction methods are tantamount to creating good places to work and live. So this is Cat Lake First Nation. So they declared a state of emergency where 87 homes were declared uninhabitable. So just wanted to focus in on one community. So this is a photo of a wall inside a home in Cat Lake, taken in 2017. The photo is part of a presentation to the federal government officials at a meeting with Cat Lake. So Chief and Council does regularly meet with officials. We'll know that many First Nation communities are in areas that were certainly not selected by us through colonization. You know, as Indigenous people, we're very nomadic, so we didn't select the areas where First Nation communities currently exist. We traveled with you know, the harvest season. If we were moose hunting, we would follow the animals. We didn't necessarily live in one spot. We're very nomadic. And I think what happened during colonization, not I think, you know, what happened during colonization is the government selected areas, plots of land where First Nation people would exist. And quite honestly, they're not these beautiful locations, and many are in swampy, wet areas. If we look at Szechuan, they're always evacuated from their community due to it could be flooding because they're on the river system. So certainly not the most ideal of locations. So in these areas, moisture is certainly an issue. So one of the things too is just improper storage of sheets of drywall means that some homes are moldy before they're even built. So if you think about some of the equipment that's brought up to northern communities before they're even put to use, they're moldy. So essentially, when someone gets a home built for them, as soon as they move in, the house is already moldy. So First Nation communities are often an afterthought. So now's the time to dedicate research and effort. So this initiative is truly reconciliation in action. I'm just going to stop sharing because it's really weird for me to be not seeing people as I talk because I'm very relational. So I just whizzed through my presentation so that I can actually have a conversation, not feel as though I was talking to myself. There's other things I think for me that I feel personally committed to this project. My aunt who lives on Chapel Cree First Nation was doing a bit of renovations in her home, and there was a bout of blastomycosis. So blastomycosis is another another area where it's really affecting First Nation communities. So we thought she was going to pass. She was in the hospital in ICU for many, many months. She had a tracheotomy. We never thought that she would survive that, you know, horrible health concern. And you know, she's still with us today, but residing in the same home. So there's a lot of barriers, a lot of issues, systemic issues that impact Indigenous peoples. And, you know, it's important to understand that many First Nation communities, there's lack of adequate housing, lack of health, lack of concern from many levels of government to inject resources to be able to assist communities. Because I think if there was some concern, we would be in a better spot. You know, there's a lot of issues I can talk about in terms of health, lack of adequate water. So many First Nation communities are still under boil water advisories. So the fact that they can't even wash or drink in their communities is wild. And where they do get water, bottled water, a case can be up to $50. So just the inequities that exist in and around northern communities is really important. And you know, just very grateful to be here. I can go on and on and on. I'm sure that you know, Shivika, Jean-Jacques, and Wai Ping have already heard me, but I'll pause in case there's other comments or questions or thoughts that people want to share.
Thank you, Christian. We will continue the presentation and then we have some questions.
Wai Ping, I
Okay.
had a question if that's possible. Thank you, Christine. Kristen, sorry. That's really interesting and concerning at the same time. I'm curious to know, so I'm Hélène Carabin, I'm a professor at Université de Montréal. I'm also the Canada Research Chair in Epidemiology and One Health, so I'm really very much interested in the health of all living things. So I'm curious to know, in these communities, has these problems also affected the animals of people living in these conditions, which would then add another burden to them, because they would also have to take care of sick animal. Blastomycosis affects dogs or cats just as much as they affect humans. So, you know, seeing the problem as a whole makes it even more of a problem, in my opinion, and something that really needs to be solved.
Yeah, like I'm no expert by any means, but I think you bring up a great point because, you know, as Indigenous people, we live off the land. So we get our food source off the land. So if we're eating or harvesting animals that are on land that is, you know, poses a great concern. And one of the communities I didn't sort of hone in on is Constance Lake First Nation that had, you know, while the coronavirus, like COVID-19 was occurring, they were also dealing with blastomycosis, and there was also child deaths in community. So it really hit hard. And so this is the community that I had talked to Wai Ping about really working alongside. However, as it relates to First Nation communities, they've experienced a number of deaths recently. And what happens in First Nation communities when there's a passing of a community member, the community shuts down. So for me to try to have these conversations about this work while they're grieving would be really insensitive. So, you know, we've met recently, and I you know, suggested to Wai Ping, perhaps I'll just reach out to the broader collective because I don't want to create harm while we're doing this work. And it, you know, First Nation communities are really relational. So, you know, if we move too fast or try to impose, you know, the project on them in a way that's disrespectful, you know, it could halt the work. So I appreciate that question. Now I'm really intrigued to know about whether or not they've experienced or noticed a difference in the food sources in terms of animals in the area. And I apologize, Wai Ping, because I said, is there any questions? But really, I should have passed it back over to you and you should have continued the presentation. So I apologize.
But that and their dogs and cats. And just by the way, I do have a person with whom I did my vet school, Charlotte Sauvageau. She's in Timmins.
Okay.
So, you know, maybe there's a way of thinking
I
about
love that connection. See, I
Yep.
love that.
Yep.
Awesome. Cool.
Wai Ping, are you there, guys? Can't hear you. Okay.
Making Yeah,
Okay.
I'm co-host. Are you already a co-host?
Yeah.
Okay, just share your screen.
Well, thank you, Wiping. Thank you, Kristen. And thanks all of you. I'm gonna hold these because I don't have a podium. All right, so I was actually inspired by John yesterday. About, fear, uncertainty, fear, and impacts. And I thought that was a really nice way to sort of frame sort of what we were talking about. And there's lots of overlap actually with the conversation that we just had with Kristen, which is awesome. Kristen and I work together on different things and we seem to think alike on some things, which is very good for me. So in terms of context,
Excuse me,
Yes.
Jean-Jacques, could you be a bit closer to the mic? It's a little bit.
is this the mic?
difficult.
Is this the mic? I'm not really sure.
Oh, this is much better. Thank you.
This is much better. Oh, I feel like
Yes.
Beyonce or something. All right. All right. So just a bit of context, and I'll sort of fly through some of this. So in the news, we talk about a housing crisis, right? The affordability crisis, but there's a less publicized housing crisis, which is the crisis of mold, where mold is at the center of it, right? So Kristen did mention that black mold is almost a misnomer because mold can come in different colors, although black is often one that we associate with. In a 2012 research article, the conclusion was historical factors that are part of the legacy of colonialism have contributed to mold-related housing crisis on reserves, especially. So we know that mold doesn't discriminate, right? It's not going out after houses on reserves. It's going after organic matter with high humidity within a certain temperature range. And it turns out that the lack of proper build and maintenance of houses on reserve are especially vulnerable to this, right? So we're talking about over 40% of housing on reserves being mold contaminated, right? So I don't want to give you some numbers. I mean, it helps me anyway. So Indigenous refers to 3 different groups: First Nations, Métis, and Inuit. $1.8 million as to our last census of 2021, 18.4% of that being of that number, Indigenous populations on reserves, just to give us a sense of scales, right? So I think we all are familiar with the idea that Indigenous life is characterized by, and this is a quote here from Indigenous Services Canada, significant and long-standing gaps in socioeconomic outcomes, right? So this is the 40% number, right? As compared to just under 10% in terms of, the general population on average, right? So there's going to be other segments of the general population that are also more impacted by mold in the home, specifically low-income individuals in subsidized housing concentration. So the number would be something close to the Indigenous on reserve number in a system like a TCHC, which is Toronto Community Housing Corporation, right? And just to note that you can spell it with a U, right? In Canada, we're always flipping between British and Canadian spelling. So City of Toronto tells us, right, 270 species at least of mold have been identified in Canadian homes. So mold releases spores, right? And that can be inhaled. And this is where you really get the respiratory morbidity. You could also brush up against it and you get some skin morbidities. In fact, there's 2 studies that were done in 2023 in Northwestern Ontario with communities on both of these issues, trying to understand the mechanism really of fungal infection, from mold and mold spores. So common conditions include for exposure to mold in humans range from skin conditions, atopic eczema, to respiratory conditions of severity. Children and people with weakened immune systems are most vulnerable. There is some association with neurological conditions. Obviously, anything can lead to death, left unattended. But these are a bit more sort of like contentious, right? But when we talk about people with weakened immune systems, of course, we just went through and still going through in some ways, COVID, and COVID has resulted in a degradation in the immune system for large segments of the population. This opens the way to mold as a secondary infection. So I think Wiping is going to speak more about this, but Of course, climate change is something that we think about because mold really thrives in areas of within a range of humidity and temperature, and climate change, of course, changes that equation. It helps us understand the dynamics of that in terms of geographic distributions. With a large scale, now, while a large scale fungal epidemic is deemed unlikely in humans, mortality rates are pretty high, like when that happens, right? Up to 40%. And fungal epidemic is more likely in plants, insects, and some animals. So animals are also affected by this. And so the One Health approach, which we all sort of committed to, is this is our time, right? Because indeed, this approach is in fact needed so that we can understand the interactions between fungal infections, humans, animals, and plants. And even there was one case that I could find in last year in Calcutta. So this person actually is he actually works with like he's a researcher that works with fungi and mushrooms, and he seems to have exhibited a plant to human fungal transmission through like a long exposure. So this is very, very rare, but this is something that happens. So Kristen, you mentioned Cat Lake. So Cat Lake is one of these cases that if you start sort of like poking about in the media, or perhaps you remember in 2019, right? So this community is just the north, just a little west of Thunder Bay, about 600 kilometers. At the last census, a population of 651. So it's a growing community. The previous census, it was 15 people fewer. So this created a real stir, if some of you may remember this, because of what Kristen mentioned, like a really acute cases of mold contamination that resulted in horrific. I sort of thought about showing you the pictures, and I thought, well, if you want to see horror, you can look it up, but really horrific skin conditions in very young children. And this animated the House of Commons, and one MP, Charlie Angus, called the conditions horrific upon a visit when he was invited by the community to sort of see what's going on. And when we talk about sort of public policy interest and impact, he said something that was just really echoing what the community's been saying for decades. Cat Lake is the tip of the iceberg because there are communities across the country that are suffering from a mold crisis. And I just want to mention that, there's three kinds of this. This has been going for a long time. Kristen mentioned this Saskatchewan. I happened to work on the Saskatchewan case from a policymaker perspective because I happened to be at the Ministry of Finance in Ontario at the time, 2006. Saskatchewan was moved. The community was moved by the federal government to a floodplain, right? Which is a James Bay community. So every year there's a flood because it's a floodplain. That's what it does, right? So why, they would have moved them there is hard to be neutral about. In any case, in 2006, it really sort of came to wider public understanding just because that flood was especially, impactful, and folks had to be evacuated. The community residents had to be evacuated. And for the last 17 years, every single spring, the community has had to be evacuated. And of course, these are the ideal conditions for mold. So you would not be surprised to know that homes in Saskatchewan are largely contaminated by mold. Kristen mentioned Cat Lake. So I should be fair to the federal government and say that they did supply homes to Cat Lake about a year after. Go ahead, please. They did supply some homes. They replaced the most damaged ones, but the community still suffers from a housing shortage, right? And the conditions that have led to mold contamination haven't changed. And so we can't expect that that's going to necessarily be a sustainable solution. And I mentioned, I think briefly, that 4 communities in the Sous-Local areas, Indigenous communities, that's northwestern Ontario, so same kind of general geographic area from us Southerners, but still very far from each other, have been studied in the last few months. At least the papers were published in 2023 to try to understand the link between mold, exposure to mold, and respiratory and skin morbidities. And frankly, the results are sort of like inconclusive in some ways, certainly on the skin one. So more on mold. So I think, not much to say here except that humidity, temperature, and the substrate, so the substance upon which mold grows, is really important for understanding the likelihood of it taking hold. As you can see, I'm trying to not repeat things that were said. So there's the drivers in terms of the sort of environmental drivers, the temperature, humidity, and substrate. But there's also some socioeconomic drivers, right? And that's where thinking about the history is very useful. So there are sort of socioeconomic reasons why the build quality of the structures are what they are, right? The state of repairs we talked about, and overcrowding as well. So, okay. So some policy imperatives. So we're really interested in, at least I'm very interested, wiping as tasking to sort of think about what the policy relevance and impact of this would be. So for sure, more research is needed to understand which species of black mold, or really we should call it toxic mold. I mean, so I'll sort of go back and forth between these appellations, are prevalent in specific indigenous communities, right? And so that we can understand also the link between these specific species and health impacts experienced. So the policy impact, the policy interest is motivated for the health impacts, of course, and equity considerations, right? Given disproportionate impact on certain segments. So we're going to focus in indigenous community, likely specifically on reserve. But as I mentioned, mold doesn't discriminate that way. We discriminate as human beings, right? We discriminate in relation to other human beings. And so wherever those conditions prevail, such as TCHC housing, for example, you get the similar problem. So policymakers should also consider the cost of erosion of housing stock. Now, I'm thinking more from an economic perspective, right? We're thinking about, but even from the economic perspective, at a time of declining new housing starts, erosion of capital stock is something that policymakers may also be concerned about, because these are really because this having a lower than required rate of maintenance is a large driver of this. So besides the legal obligations of the Government of Canada towards unreserved Indigenous communities, policymakers should note that preventable declines in health outcomes for the fastest rising segment of the population in an aging country is also counterproductive, right? Okay, so I'm going to skip some of this. So in terms of sort of, our next steps, so we're pretty early in this, right? We are very fortunate to have the guidance that we have from our Indigenous partners, and we're learning this. But already we consider traditional models of mold growth relied mainly on steady state kind of conditions that assume equilibrium conditions, but so we'll be looking for really thinking about more the dynamics of the situation. Also relied on statistical estimation methods, lacking location-specific experimental data. Now, this has been improving very slowly, very specifically, like, for example, the 2 studies that I mentioned in Northwestern Ontario that were published in 2023 did collect local data. We don't have access to this because in both cases, the communities have asked that the data not be released, right? These are very sort of, low numbers of community members, like, from a statistical perspective, but nevertheless, obviously the more relevant fine-grained data that we can get, it'll increase the potential to better understand causes and mechanisms. Adopting a One Health approach, as I mentioned before, is promising, right? So the need for experimental data, when Wiping speaks about climate change, hopefully he'll mention our Ontario Climate Data Portal. So we are able to do some high resolution modeling because that work has been done, and which is very useful for us. And I'm anyway very curious about what would eventually maybe turn out to be prediction maps, which is incorporate climate change scenarios to extend the model to account for the environmental models that allow us to project where and sort of when mold may reach places that it has not currently. So for example, very cold places like Northern Canada and Russia, are not currently hospitable for mold, but we're sort of creeping up. In some places will be in some time period. And the Nile Valley is expected to be much too warm for mold. So the prediction maps are going to be useful from that perspective. So in terms of research program, and I'm just ending now. We want to deepen our partnership with the Indigenous community. We appreciate our collaboration with Kristen, and through that, making new collaborations so we can understand the lived experience and also have access to data that can help us better understand the mechanisms and the causes. We're working towards a paper to really sort of bring ourselves up to date on the science, the extent, and health impacts of hold in. We're really focused here in our sort of central Canadian geography right now, just to keep things, focused and lay the foundations of subsequent papers where we can actually get into some modeling. So I want to end with, what I was inspired by yesterday, this idea of uncertainty, fear, and impact. So in terms of uncertainty, there remains uncertainties about the biology of toxic mold and the interactions with humans, and more broadly, the relevance to One Health concerns. In terms of fears, well, of course, in the context of housing, mold triggers fears in all of us, right? In terms of unhealthy outcomes, unhealthy homes, and devalued, capital stock. And in terms of impact, well, news, media, and government reports speak to impact on animal, human, and plant health and well-being. So I do want to still thank, our Indigenous partners. I want to thank you, Kristen, for your guidance and your involvement, and of course, NSERC, the OMNI community, and all of you. Thank you.
Thanks for the presentation. It's a really exciting project, and I just wanted to congratulate the team on taking the approach of starting with an issue that is of relevance and concern to Indigenous communities as a starting point, rather than with an a priori of what should or might be important. So that's excellent starting point. I guess I would echo Ellen's comment in saying that as OMNI, the One Health modeling network, it'd be important to really push the One Health aspect of this to the extent that it's relevant. And so I think what you presented is a very interesting environmental health problem, but without really any consideration of the animal component to it. And not all One Health problems have to include animal health, right? I mean, we like to look at the interface, but in some cases it's not relevant, and it's the approach that's important. But in this case, I do think that there's real potential to consider that the animal sphere, and I don't think you're going to do it by modeling hay in northern communities. I mean, think about what are the relevant animals, and Kristen mentioned, is there wildlife impact for country food, but also companion animals and other animals in those communities that might be affected. The question that comes to me though is, a lot of your presentation put the emphasis on, well, we need better data and experimental approaches and so on. And none of that is modeling at this point, right? But this is not a criticism, it's probably true. And I think generating those data in partnership would be an excellent, project in and of itself. But there's an approach called model guided fieldwork that might be interesting to consider in this context, where essentially in parallel to developing a field experimental program or environmental sampling, you do modeling with your current ability of knowledge of the system, which may include a lot of uncertainties. You identify those uncertainties, and it helps guide a better sampling strategy for doing it. And you could do both those within the project, but waiting till the end of doing all the experimental, parameter generating exercises to run the first model, I feel like would be not taking full advantage of the expertise that is in OMNI around the modeling component.
Thank you so much. And maybe I'll just summarize quickly. So Patrick was happy that we're following a community sort of identified concern, right? Has some concerns about whether we should do the approach that I sort of presented was leaving modeling for a second or third step, and propose that we consider a model guided fieldwork approach, which I think is fantastic. So thank you very much. That's wonderful. Yeah, and he also mentioned that it would be important to take advantage of what One Health has to offer, and we may want to pick up on Kristen's suggestion and look at wildlife around these communities to consider the impacts on animal health in a more direct way. Thank you so much. That's awesome.
Certainly not my suggestion. Helen brought it up. And you know,
Helen, sorry.
I have to give credit where credit's due.
Awesome.
There's a question for you in the chat.
Maybe.
I had a question for Wei Ping. I'm wondering if it would be useful to do something like a species distribution model where you find like the environmental variables that are like suitable habitat for an organism. But in this case, it would be black mold. And then you could overlay that with like areas that have indigenous communities versus non-indigenous communities. And that would kind of build the argument that this is an area of need and quantify the amount of inequity there is between like where housing is for indigenous communities versus non-indigenous communities. And then when you've sort of quantified the magnitude of the problem, then maybe that would help to bring more attention to the issue. I'm just wondering if that would be like a useful analysis.
Yeah, in fact, definitely, all mentioned was great. I didn't show details of the first page. In fact, all of this was proposed in our original proposal, but it didn't work. The only reason is we are facing the challenges to work with First Nation and indigenous community, which is very special. The majority of the funds for this SIM5, originally we didn't expect this, we didn't know this rules, but the fund will be paid to the indigenous people who work for us. We have to develop this kind of connections, and then we ask them to work with us. We want to understand their concerns, and then start from the very scratch. Also, by answering many of the discussions, the language we will use to do the research and communication, we have to use 26 language. So many restrictions. So in fact, I really feel excited because people care about, indigenous community in its concerns. But how to do the groundbreaking work? So in fact, our plan is anything greater than 0 is a great success. So this is currently the situation. So that's why we started this, with Mark and Elaine, even last 2022. In summer, we started the discussion. We tried to connect it with broad community, try to develop this kind of connections. We can even say, like, I want to come here to do the research for you, for your health and well-being. That is not right. So this, when we work with indigenous community, we should be very careful. That's why, the training program is still, we have this idea as to how to run this training, science related data literacy or modeling. This is much more than grade 6 language to do the work. So that's why we are, next 1 or 2 months, you will see we will have to rely on the support of the whole network, and then develop the partnership collaborations with people who can support us to move forward. So that is, in fact, the challenge. Also, that is also the reason, the same 5 originally the letters leading to the, we are revising our proposal to review the network to drive things move forward.
Apparently, there's some questions in the chat. I don't know if somebody can read them because
Sure, okay, open that.
just the chat.
go to the more, but. Question is, what is being done includes these guys.
Sorry, I can't hear you. And what is being done?
What is being done to increase buy-in from the affected community and that this understanding, so maybe they can show how to gather the data themselves.
What is being done?
You can see it there on the screen.
Okay, what is being done to increase buy-in from the affected communities? Their lack of trust is understandable, so maybe they can be shown how to gather the data themselves. Okay. You want me to answer? Do you want to answer?
No, I'm going on today, but this is, again, every little step is challenging, difficult. So we learn, especially I myself, learn the lesson of gain experience. So we have to be very careful, working with, the representatives, just like we do research, first look at time and then consider the spatial effect. We start from a point, a small community, develop the trust and the connection. And then moving from that small community to see if we are able to expand this, to allow more work. So this work, as to what kind of work we will need. So the starting point is that, we look at this black mold issue, because this is currently the most concern from the community. So because at this situation, from what Christian just mentioned, all in this community, they are all really relational. Now they have this concern. If you talk to them about other issues, that's not possible. So that's why we start with what they most concerned, and they start from the first community started to get the ball rolling.
I think just if I can just interject,
Yeah.
increasing buy-in is really about, connecting with me and realizing that, there was an attempt to carry out the work and it wasn't occurring the way that, you had anticipated. But by bringing me on, I think having those connections, I'm really closely linked to 11 First Nation communities just by way of my full-time work, and even beyond, right? Because we all sort of know each other through one way or another. We're cousins, we're colleagues. So that's sort of step one. And I think one of the other areas that, I can't recall if we discussed it or not, but one of the things, I will be suggesting is us following the OCAP principles. So that ownership, control, access, and possession of data is so important. And if we follow those principles as we're carrying out this work, trust will come right away. I think there is a lot of things, right? We're not being pushy and forceful. Wiping and the group did recognize that there was a death in community. So we're not going to just rush in and say we have a timeline. I think the respect and just me sharing some of the intricacies and nuances of working with Indigenous people has been eye-opening for the group, and knowing that there's ebbs and flows. We can't just rush in and do work. There is going to be relationships built. We're probably going to bring food and, come in peace and those kinds of things. I say that, tongue in cheek, but that's important before we carry out the work, right? Meeting the leadership of the community, getting to know some of the residents who have been impacted and affected, and really show that we're there to do good work in an honest and kind way, following the 7 grandfather teachings. So that's kind of how we'll certainly build buy-in. I think it will be a little bit easier, and I'm not saying I'm the conduit to all First Nation communities, because that's not true at all, but I think I have the knowledge of knowing how to connect and when to sort of back off and when to go forward. So that's sort of how we'll go through that. I do have to say I need to connect to another call, so I apologize, but I do have to run. Thank you so much for having me. I'm just so amazed, and it's really a neat project, and I'm so grateful to be here.
Okay, thank you, Christian.
Thank you, Kristen. We'll catch up because I had questions for you, but we'll catch up later. Thank you.
Next, in fact, this is my slide I prepared. I just want to do some introduction myself. this OMNI network started due to the pandemic. I want to just mention why I was interested to organize this One Health network. Like I discussed this with the when we're starting working on West Nile virus. What is West Nile virus? In fact, it's a typical zoonotic disease. It is the bird animals human infection virus. That is one. The second, in fact, in 2018, the whole society worldwide were concerned about the possible emerging pandemic or infection coming from, for example, HAPI, the bird flu related issues. And then in 2018, I was in fact in China. There was a WHO International Zoonotic Diseases Conference. I was here together with Chinese Animal Health and Epidemiology Center. So that is what I learned about the One Health. And then after that, so you see, this is the old slide. I couldn't have time to redo it. So this was December 5th, in fact, 2019. I was invited to give a presentation at the First Nation Climate Change Workshop in downtown Toronto.
It's not shared.
So I will be quick because this was prepared for that workshop. Just give some ideas. In fact, all things are still working for today because the research was somehow like changed due to the pandemic. So this was the plan. So introduce about just now, Christian and Jean-Jacques mentioned about black mold. That is only just one further issue. In fact, there are more broad concerns for the North. So I will present. In fact, we want to see what will happen in the future under the climate warming scenario. So this has three parts or two parts. One is introducing the data portal we prepared. Also, in the data portal, we specially prepared for the Northern Indigenous community to cover the future 100 of climate projections. Last one is the warming and impacts. I will give certain examples. So of course, it is important to look at the future climate change in the whole country, especially to the north. Here are some there's a pandemic Canadian framework on clean growth and climate change. And so this, let me just be quick. So this is the situation in North America. Here, in fact, just now the Christian mentioned. So in Northern Ontario, we have 2,205 reserves in Ontario. As you can see, these areas are very special. Most communities are in coastal areas in Northern Canada. So originally, we want to do mosquitoes. We want to see how mosquitoes is moving from south to north to do long-term projections of the mosquitoes and mosquito-borne diseases in Canada. In order to do that, we need climate data. Nowhere to find the data allow us to do this. And then we started to do the projections ourselves. We were lucky to have the support from the Ministry of Ontario starting of 2011 or 2012. And then the total funds now reached, I think, about 2 million for this many years. We established this, I call it Ontario Climate Data Portal. So this data portal is now developed and joint work with ministry to make it to support the climate action in Ontario. But our data portal is mostly for research purpose. So this data portal, in fact, we have the address. If you Google OCDP or under the CMOS webpage, they have a paper introduced the work from us. So in fact, I will not go into these details. I even forgot how to pronounce this names. I will just show, just show one example. This is what we look using the projections we have. We look at just one thing, one important slide to show. You see here the future projections of the climate. So you see globally, we look at future projections. We have three things to compare. One is globally the future temperature. The second is the Canada average. The third is active area. If you look at this, this is like the future using the RCP 8.5. We do nothing to see what is happening in the future till 2100. So about 90 years later, so this will happen. You will see the warming end will happen most in Arctic area, comparing to the whole country and comparing to the globe. So this was the result. In fact, this was done by 2019 because that was specifically prepared for this workshop, for that workshop. So in fact, we generate a lot of comparisons leading to, let's skip this. Leading to the build-up of the data portal. In fact, this data portal is we have 20 terabytes of data covering the future. Also, we have the historical data to cover not only Ontario, but also part of the Eastern Canada and part of the New York State. With that, we want to do impact studies. So one is we want to see how this West Nile virus affects the Northern Ontario. So this is the map. So we generated. Currently, it is, you see the warm area suitable for mosquitoes, especially Culex mosquitoes. And then by 2050, 280, you will see the area moves to the north. So this will create, currently there's no mosquitoes, Culex mosquitoes in those areas. Maybe in the next 30, 50 years, you may see those mosquito creatures will be there to bite people, of course, and animals. The other issue is not only animals, not only the mosquitoes, but also the agriculture. This is the corn field. So this is the map. Currently, you see the blue one is under here, like it growing corn. Up to the north, you see that is the land not suitable for agri yield. So if you look at something called growing season length, GSL, and then using the projections we generated, look at the situation in Ontario. So this is what is happening. This is like the current situation. This is by 2050. So this is by 2080. Basically, in the next 50 to 80 years, you can imagine the northern part, many places will be ideal for growing corns and other, agri plant. So this again, this was the project is done using the data we generated in 2018. So with this data portal, we also look at the emerging, for example, now we have local Culex mosquitoes, but we care about, for example, the dengue, chikungunya, and the other type of mosquito-borne diseases. Those mosquitoes are coming from south, from states, and then moving up all the way up to the north. So now they are hesitating at the border with Canada and the USA. We want to look at will those Aedes mosquitoes keep moving to get into Ontario and then move up to the north. So we did some research. This is like this is currently the Southern Ontario. You see the movement of the Aedes mosquitoes. So this is by 2040. You will see certain areas started to emerge, to merge the mosquitoes, and then by 2100, so this is part of Ontario, those mosquitoes, Aedes mosquitoes, will become active and also can transmit like malaria, dengue, chikungunya, those kind of mosquito-borne diseases. Also, at the beginning, I was somehow very naive with the thing. If we are able to look at climate change, mosquito species, and mosquito-borne diseases, we can do many things. Of course, things are different. But as a byproduct, in fact, in 2018, in fact, we worked on a paper. At that time, we look at the Great Lake area, the maize reproduction in the whole Great Lake area. At that time, the paper was in preparation. Now the paper is submitted to Nature Communications, is in the review. Most probably it will be accepted. So this is, in fact, we look at up to the north, and climate change, what will happen to the crop yield. So this is one of the examples. Of course, at that time, I didn't mention, the animals, the common health, One Health in this yet. This was, in fact, exactly like Christian mentioned. So this was, where's the date? You see, February 15th, in 19. In fact, there was a lot of report about that. In Cat Lake area, 87 horses were turned down. Due to that, in fact, we did the calculation. So extreme climate indices for building code in Ontario. So this is, in fact, like, Climate Action Ontario, they use our data in their booklet. Also, we contributed to the building code calculation in Ontario. This, in fact, will be helpful if you look at the black mold issue, housing and climate change. So this would be most important step in the long run, what the government should do to settle this indigenous community for a better housing. In order to have a better housing, you need to know the future climate, and then we have helped them to update the building code. So this is, in fact, just give you the idea by 2019, the whole idea, when we look at the climate, the impact the climate for the northern communities, which is pretty much in line with what we will do. But this kind of things, again, we have to be very careful. So that's why I haven't really been able to, for example, prepare a similar slide for this. So just use this to serve as to give you some ideas about the related research. So I will stop here. Let's see. Yes, please.
Yeah, no, thanks for that. I can't believe Lisa called this presentation really interesting and thought-provoking. And again, the thing that this was done just before COVID also makes it quite just in many ways. But looking at the maps that you showed, and particularly the a potential economic boom from agribusiness as the amount of arable land increases. I wonder if you're teaming up with folks in economics to look at what the trade-offs are in terms of, okay, there's an increased risk of disease on account of these vectors, but then an increased potential economic boom from agribusiness, and to the trade-offs in terms of how much will it cost to prevent disease and versus all economic, shall I say, benefits that could come in terms of jobs and finances from the agribusiness expansion. Could be quite interesting.
Yes, I think in fact that is a plan. We have so many things to plan to do in terms of land health, human health, animal health, agri-yield. Even we were contacted by the Canadian Railway because they are building new trains to the north. They asked us to project what will happen, how deep we should dig to build the railway such that this railway was sustainable for 100 years. So those kind of things. But with this, what I want to say is, it's late already well for the future impact studies in the northern community and areas. So with the maize production, now the OMNI, Ontario Agricultural Community of Ontario, they are asking to have a copy of the paper, because this will change the future vision of agriculture in the country. Of course, it will change almost everything. So any more questions? In fact, like this is just the starting point. There are too many things to think and plan how to move the city pipe forward. So please be patient. Also, please, yeah, yes.
I was just, I think it's a good time, good idea. Your team might see on that because there's quite a lot of work going on team on things with other, so the risk of ex-ante vector-borne diseases, but also the endemic possibly looking at not only climate change but land use change, because obviously the risk of West Island is not just that, the climatic factors that are affecting possibly the life cycle, but that life cycle is susceptible to weather and climate depending on the environment. So they're developing a number of tools to look at that. So I think it's a good idea just
yeah, in fact, the map I showed for West Island situation, we worked on in 2012, 2013. Those papers were. I have 3 PhDs. After finished this, they went to a bank to work to earn money, but that's my mosquito career. Seriously delayed. Now we should do. We should take a break. Maybe we take a short break. When do you want to be back? What was there enough time? Started 5 minutes ago. 5 minutes, maybe a week, 2 minutes. No, so we'll be back at 10 o'clock. How are you? This is how I do now.
Theme 3, which is last but not least, I would like to say, and we're in the home stretch here. So I'm going to make a short presentation about theme 3, and then we're going to have a few people make presentations. So theme 3 is early warning systems of infectious diseases. Have this up here. So these are the projects: disease digital surveillance, signal detection, network approach for modeling spread, process to structure for early warning signals, determining a characteristic structure with multiple early warning signals, mobility-based spatiotemporal modeling for spread, and data mining and early warning signals. So the idea is that when a disease is just emerging, maybe there's signals we can pick up on either in the disease itself or on things like social media or other aspects that then can tell us what's going to happen in the future. So we kind of reading the tea leaves here and trying to actually make a prediction, whether it's 3 weeks in the future or a month in the future, or even longer than that. So it's a big challenge. So we have been active. We've recruited 10 HQP at levels from MSc to postdoc. And we have 10 published manuscripts, 2 in review, 4 in preparation. And we did come together and write 1 white paper also, which I'll tell you about in a moment. Many presentations and seminars, conferences. It's been exciting to be part of this for me personally. I'll tell you a little bit about this one paper that we put together, which is a white paper. And it's not really restricted to theme 3. It actually goes beyond the themes and beyond OMNI-RÉUNIS to include the other emerging infectious disease network. And we had a meeting at Banff where we were trying to chart the future for emerging infectious disease modeling in Canada. And we wrote a white paper, which is publicly available on this, with the idea that we need to work together. We need to coordinate as researchers all the way across Canada in multiple different ways with public health, with government, with academics and others to have a coordinated strategy, perhaps an institute that could be pan-Canadian. And so that's articulated there with a lot of thought, bringing all these different folks together. And I would encourage everyone to take a look at it if they're interested. So this is, in my belief, one of the big challenges that we now face at the end of this cycle of funding. In terms of the research from theme 3 in particular, we explored early warning signals in things like epidemic processes and social processes. And we tried to understand it in terms of the underlying structure of disease transmission and the things we can measure, available data, social media influence, and so forth. We also included travel and things like that in our modeling of the outbreaks, and try to connect to the internet because that's our information superhighway. And you'll hear more about that in a moment. And some of the methods that people have developed recently, of course, are based on deep learning. So deep learning is very good when there's lots and lots of data. You will see this when you see the presentations. Sometimes there's not a lot of data. And so sometimes deep learning is not the best way to go. And statistical methods may be better, maybe less sophisticated, but more robust in some sense. We designed and evaluated data-driven recommendations of models based on geography and other things like that. And so that's the summary of our research. And what I'm doing here is just moving, yeah.
So when the people online cannot hear you, let's check with the link. It's not here.
I think the microphone might be muted.
No, I can hear fine. It's fine.
Okay. Is there anyone that cannot hear? Okay, we're good then. That's great. I'm glad you checked though, because that would be a pity if we lost people online. Okay, wonderful. So the way we're going to do this is we have all the slides in a single file to make life nice and smooth. And I'm going to invite the speakers to talk. And when you say next slide, I'll push the button. And so we're starting with Zahid Butt, and these are the slides for Zahid. So please go ahead, Zahid.
Thank you very much, Mark, and I would like to thank York University as well as the OMNI-RÉUNIS network for providing me the opportunity to present my research. Just a brief introduction. I'm an assistant professor at the School of Public Health Sciences, University of Waterloo. I'm also a Canada researcher in interdisciplinary research for pandemic preparedness. So today I'll be talking about digital disease surveillance for emerging infectious diseases. And as you can see from here, like we'll follow a kind of like an outline starting with background, and then at the end we'll talk about future work, which is also ongoing work that me and my group is currently doing. Next, please. So as we all know, emerging infectious diseases are a significant threat to population health globally, and we have seen that with COVID-19. We have also seen really a rise in the use of internet search engines and social media, even before the pandemic, but actually more during the pandemic. So the project was based on thinking that maybe we could use some of these search engines or social media such as Twitter, which is now X, to actually see if there is a relationship between emerging infectious disease and what people search or discuss on social media. And this can actually help us in developing a real-time or near real-time surveillance system from search engines and Twitter that can actually predict or forecast emerging infectious disease. Next. So our objectives were, first, we wanted to know if there was an association between internet and social media data with COVID-19 in Canada. We wanted also to see if somehow we can predict or forecast COVID-19 cases in Canada from internet search engines and social media. And the ultimate goal is basically to develop a real-time surveillance system for the prediction of emerging infectious diseases such as COVID-19. So we kind of used COVID-19 as a proof of concept to try to see whether it works well using this sort of data. Next. So what we did, because our focus was more on early warning, so we actually extracted data from Google Trends and Twitter at the beginning of the COVID-19 pandemic, from January 2020 to March 2020 in Canada. We did an extensive literature search for certain keywords that we thought might be useful for us in our models. So for Google Trends, we actually looked at the symptoms, which, as we all know, they have cough, runny nose, anosmia, sore throat, and most of the common symptoms that you see in COVID-19. And for Twitter, we used COVID-19 related hashtags such as pneumonia, cough, runny nose, and breath. So we we use these keywords. COVID-19 data was obtained from the COVID-19 Canada Open Data Working Group. Next, please. So before doing all that, we did some data pre-processing. So we used some methods actually to remove you could say, the white noise in the data. So we use these following methods before we started analyzing and using the other methods. So we used a time lag cross correlation analysis to examine the relationship between each signal, and by each signal we mean like the data that's coming from Twitter as well as Google Trends and daily COVID-19 cases. And we wanted to see if there is a kind of an association between what when we use the keywords and see with the surge of COVID-19 cases. We also used a deep learning model, which is a long short-term memory model for forecasting COVID-19 cases. Next, please. So as you can see, this is a graph which shows you could see the results of denoising, or you could say removing white noise, where we use different methods. And you could see on top that there's a raw data on Google Trends, and you could see that when we used a denoising procedure, what does it look like? And similarly, we did it for Twitter data as well. Next, please. So when we did the cross-correlation analysis, what we saw that, as you could see that the coefficients for the different signals, that is the symptom keywords, they really actually kind of started from ranging from minus 0.275, that is for fatigue, and then really went up to 0.825 for cough, which is more characteristics with what you see with COVID-19. And on the left side, and similarly for tweet as well, we use symptom series as well as COVID-19 hashtags, and you could see that you could basically see that the time lag cross correlation analysis between Google Trend signals and daily COVID-19, they show a range of 1 or 13 days of time lag, which if you think from a perspective of early warning system, if you know about, if you can see these sort of trends from these signals, you can say that, well, approximately we could predict a surge of cases in a sense 7 to 10 days before the cases really come up. Next, please. So we also used a long, as I said, a long short-term forecasting model. So what you're seeing here is basically a kind of the results of a long short-term forecasting model. On the left side, you can see the daily cases, and then you could on the x-axis you could see the number of days. And what you could see here in the graph is that the orange line, which the blue line is basically the true values, and the orange line is your predicted values. And we can see that using your long short-term memory model with a correlation coefficient of more than 0.79 really predicted these COVID-19 cases well. We also experimented with different subsets, of features. We try to combine different features together. We also, it's not presented here, but we also looked at public health interventions and tried to see how good are they in predicting. But this is what we found in terms of performance was the best performing model. Next, please. So, as I mentioned before, we could see that COVID-19 symptom-related surge terms strongly correlated with daily COVID-19 cases with a time lag of 1 to 13 days, depending on what symptom keywords do you use. From our results, we found that both Google Trends as well as Twitter data can serve as early warning signals for real-time digital disease surveillance. However, when we look at the LSTM model, it performed better using the Google Trend data than the model using Twitter data, or a combination of both. Next, please. So we were able to publish something, about our study, on digital disease surveillance for emerging infectious diseases. We were also able to present that at various conferences as well. Next, please. So our future work, which is also kind of ongoing, is to basically develop an ontology-based keywords to systematically identify and organize symptom keywords for an emerging infectious disease, even before they are commonly recognized or reported. So what we are thinking of is actually working on looking at the different infectious diseases. And as we all know, COVID-19 and flu or respiratory pathogens, and they have similar, basically, in a way, symptom profile. So we're also thinking of actually doing this for other outbreaks, such as, let's say, we do it for like foodborne outbreaks or some other outbreaks. We also are in a process as actually getting some data from CAIHI, some hospitalization data from CAIHI, so that we are able to look at how good social media and other internet search engines can predict hospitalizations. That's also under process. The future, we are also thinking about looking at the relationship between search trends and public health interventions like lockdowns, vaccination campaigns, or policy changes. Next, please. So I would also acknowledge my colleagues who were working on some aspects of the digital disease surveillance with me from our department, as also from computer science department. Next, please. So thank you for listening, and happy to answer any questions.
Thanks, Zahi. We have time for a question. Are there questions online?
Chat.
In chat. Okay. Well, I think that's been there.
Oh, I
Yeah. If there's a question online, please just speak up and say it. Okay, great. Oh, Patrick has a question. Sorry.
Just a quick question out of curiosity, it seems like using Google Trends sort of work, you know. It would be a really powerful approach. I was just wondering if, as you publish this work, you had a sense or connected to any other groups who've been doing similar things for COVID, and if they found similar results, I mean, in the US, or, I mean, is this, are there other groups who've attempted this?
Did you hear
Yeah.
that? Yeah. Okay.
Yes. Yeah. So there might be other groups who are working on this, but we haven't had a contact with them. So just to answer your questions, and yes, like I do think that Google Trends has a lot of potential, and as we all know now, with Twitter and X, what has happened is that if you want to access their data as a researcher, it's quite expensive. So I think from that standpoint, yes, and I do recognize like some of the work in the upcoming slides might be helpful to us as well, especially the ontology based work that is the next presentation on, like how can we go about doing that sort of work, and maybe we can work together to advance this forward.
Yeah, thank you. We'll save further questions till the discussion at the end.
Thank you.
Ghazale, are you there?
Yes. Hi,
welcome.
everyone. Good morning. First of all, so sorry about the camera, because my camera got problems, so I couldn't turn it on. And I'm very happy to be here with you all. And so far, thank you so much for all valuable knowledge about this area. I worked as a postdoctoral fellow. My name is, as you know, is Ghazale, and I worked as a postdoctoral fellow under the supervision of Prof. Ayjun. And the project that I was involved related to the signal detection from social media, and we published an article, one of the publication named a hybrid outbreak detection using ontology-based data collection from social media. Could you please go next? So far, we discussed about earlier that how much early detection of the infectious disease is important and can play a very important role based on our recent experience with the COVID-19. We know that how much is important to detect the outbreak earlier. So on the other hand, we know that in our daily lives, how much the role of the social media is by the time is growing, and most of the people share their knowledge, their thoughts via different social medias. Also, we know that some of us may be familiar with the ontology as a very powerful knowledge base. So based on these introduction that I just mentioned, we provided some objectives for our project. Could you please go next slide? So we identified, why it's all one, sorry. We defined these objectives, investigate the traditional and artificial intelligence-based methods for outbreak detection. Then based on all these investigation, we tried to provide a survey article and then identify the role of the ontology for extracting the data from the social media, and then identify the role of the social media on outbreak detection. After that, we proposed a novel approach for ontology-based, is the hybrid approach for detecting the outbreaks. And after that, we provide an article and submitted and published an article. Next, please. For our first two objectives, we provided a survey article submitted to the ACM transaction on computing for healthcare, and we received the first round of the comments, and we submitted for and waiting for the final decision. Next, please. And then for the hybrid strategy, actually, we, as I mentioned earlier, we use the ontology as very powerful knowledge base for identifying the symptoms related to the infectious disease to collect the data. And we just focus on this duration, 2012-2022. Then we filtered the tweets based on the reliable sources and some methods that published in ACL to filter the unrelated tweets as well. And also we know that some of the symptoms like headache or something like this also can be used as sarcasm in some of the tweets or sentences. So we extracted and removed all of those and then grouped them, the tweets based on the location and also different location and different diseases that we had for the duration between 2012 to 2022. We just selected 6 outbreaks for this duration for the sake of the testing and having some results. And then we used time series analysis and provided one hybrid model, XGBoost bidirectional LSTM, for detecting the outbreaks. It means predicting a number of cases. And then we submitted to the IEEE BIBM conference and published there after that. And it has been selected for the special issue to be submitted as an extension for IEEE TNB journal as well. Please next. For our hybrid model, we actually provided these 4 contributions. The role of the ontology, how much ontology can help us to extract the related tweet from the Twitter. Then how our hybrid model can predict the number of infected cases using the Twitter data and also the symptoms as the keywords earlier than what reported was by health authorities. After that, how we can use previous outbreaks, the pattern of those for the future, that if in the future we can see some signals for the outbreaks can happen similar to previous ones. And then how our machine learning model, the hybrid model, can outperform some other state-of-the-art algorithms. Next, please. So if I want to give you a very general idea that what is happening from the sake of the sample data set, as I mentioned earlier, we just picked 6 outbreaks, and these are our different outbreaks related to different diseases for these locations. And if I want to give you a brief overview about what is the preview of the data set, this is very small example. This is the date. These are going to be the list of the symptoms that definitely they are going to be more than this. I just put some of them here. Then we have the case numbers. And we are in the next step, we are going to train our machine learning models based on these data. Could you please go next? Okay, so this is the proposed framework. First, we identify the symptoms from the ontology because we know that some of the keywords like tiredness, exhaustion, fatigue, all of these can be used for the same purpose. So having all of these keywords make our data collection stronger. So we use ontology as one of the subclasses of the ontology is the symptoms of the infectious disease. So we identified all of those keywords and extracted data from the Twitter. On the other hand, we have the number of the infected from the actual infected cases for all of these 6 different diseases. We collected them from health authorities like CDC, WHO, or something like this, and we created our data set. Definitely, we applied some data cleaning, filtering the data set to remove the noise and also unnecessary tweets. And then we convert them to time series data set. The time series data set, after normalizing, providing, because for each of these diseases, we need to identify the lag or the proper lag, that how many days before can be related to the number of cases. And then we trained our XGBoost model based on this data. And the XGBoost here, as is very powerful for identifying, as you know, I just showed you, we have multivariate data sets. So as we have a lot of symptoms, finding the correlation between them and identifying the important features is very important. So the XGBoost can pre-process the data efficiently and reducing the dimensionality and noises in the data set. So we use the XGBoost as the boosting actually factor to improve the bidirectional LSTM that can be trained, which is the LSTM that can be trained from forward and backward and find all of the temporal relation between the actually time and also the number of infected and the number of symptoms. And then we can predict the number of confirmed cases for each of these diseases. Could you please go next? Sorry, next, please. Okay, thank you. So our first contribution was related to using the ontology and not using the ontology for collecting the data. And as you can see, we tried and tested our model based on 3 data sets. The first one is using the ontology for collecting the keywords, which is going to be 65 keywords. It means that 65 symptoms. And then we use just some name of the disease, and just based on some of the keywords and symptoms reported by health authorities, which is going to be 18 keywords. And then another data set is just based on the disease names. So as you can see, based on these, for each of these diseases, we provided the output and the metrics for show the performance of the model. And the first data set, which we have higher number of the keywords covering by the ontology, showed better performance rather than other data sets. Could you please go next? The second objective that, as we had, is related to predicting the number of cases accurately somehow, also having them earlier. And as you can see, based on the data set for the USA, although we have the similar result for all of the data set, but for the sake of the time, I just put as example for one of them, but this pattern is applicable for all of the different data sets. So for the here, as you can see, the number of predicted and real are somehow very near to each other. And I just focused on very short timeline to show you here for the COVID. As you can see, even we predicted 4 to 6 weeks earlier can find the and predict the outbreak. Next, please. The next one is our data, our model first have been trained based on 2015 outbreak that happened, H1N1 happened in India. And based on those patterns, the model could predict the 2017 H1N1 India. As you can see, this is the real number and the predicted value by our model. It means that the model even can predict very accurately the future pandemics based on the previous data and signals that we have and data from the Twitter. Please next. And the last is our model, as you can see, can outperform some other state-of-the-art and some other models. that we can see in this table with these mentioned metrics. Next, please. So as a conclusion, we can see how social media, specifically Twitter, significantly help us to in this surveillance. And as one of the person, I don't remember exactly the name, but asked about the Google trend. Also, I found some other publications that so far the Twitter data in case of for our specifically scenario, Twitter help us and give us better performance rather than Twitter. And maybe for our extended version, also we are going to work on this as comparing the Twitter data and also the Google trend to see which one can give us better performance. And then the ontology-driven identification, how ontology can help us to improve the accuracy, how we can potentially predict the future pandemics, the early detection of the outbreak, and the hybrid model, how can outperform a state of the art. Also, in some cases, we can identify some unknown disease. Why? Because we just focus on the symptoms. And when we have this trend of the symptoms, like our two previous slides, we can, like H1N1, we predicted without the name of a specific disease, we predicted something is coming similar to the H1N1 in the future. So thank you so much for your time, and I'm here to answer any question.
In the interest of time, we'll move to the next talk, which is by Junling Ma.
Hi, everyone. Sorry. All right. Hi, everyone. I'm going to talk about the work that I've been working on to understand how, if we know a region has a case, when we would expect it to be imported to other cities or regions. Next, please. Yeah, so this is based on a work I presented much earlier, roughly the same time as the pandemic started. The idea is to understand spatial connectivity and spatial movement of the cases. We most likely would need to use a patch model or a multi-group model, etc. And so we need to understand the dynamics in each region and how they're connected. But the basic idea is if we think about how individuals infect each other, we don't care about the viral dynamics in each individual when we look at the population level. We just abstract the individual's viral load, for example, transmissibility, into multiple states like susceptible, infectious, recovered, or exposed. And we can do the same thing, right? So if the city has no individual, then no patient, then it's susceptible. With patients, but not exporting, we can say it's exposed. But when they're exporting cases, we say they're infectious, etc. So we can do the same thing, and we just look at each city, label their states, then look at the transition between the states for each city, and then we look at how these states are connected. So a city exporting cases to another city would basically mean that it's infecting another city. So use this idea, we can just look at the city as a contact network. Actually, it's a city network. They're connected by transportation links, for example. And then we look at how fast the cases would export from one city to another. And if we're really interested in the disease importation, it's in the very early stage of the epidemic. Well, from all the historical data, we can see that disease importation happened when the cities are still in their exponential growth stage rather than dying out. So we don't really need to worry about when a city's epidemic has died off. We really just need to think about the transition from the susceptible to infection state of a city. So we can just study the SI dynamics, and we have constructed a way where we can just write down the, so this is, you can think that the disease spread on the network is a Markov process. And how do we solve this Markov process? We have a specific way to write down the analytic solution of the Markov process, which we call the S-digraph method. Once you convert from the city network, the graph, into this S-digraph, we have an algorithm that can just write down the analytic solution of the problem so that we know that the time distribution that a city will have an imported case. Next, please. So can we use this method? One of our honor student, Zaresh Waji, she's currently a master's student at SFU, has worked on this for a very simple city network. We have looked at the 5 health authorities in BC, and we found the representing cities in each of the health authorities. We construct this network, which is basically a complete graph. We looked at the first date when the city is infected or has a reported case. Here, of course, Vancouver, not surprisingly, has the first case. Then we see that it starts to spread out into other health authorities. And we use this idea to construct the S-digraph and figure out, well, what's the probability that each city is infected, specifically in this order where Vancouver is infected, and what's the probability that Kelowna is the next? Then given Vancouver and Kelowna, what's the probability that Abbotsford is the next, etc. So we have this formulation. Oh, there's the I of t is missing a bracket. Sorry, it's the bracket of SI minus SI at t plus 1, then times the product. But anyway, so then how do we model the transmission rates between cities? Then we just use the well-known gravity model where the NIs and NJs or the populations or economical factors like GDP of a city, D is the distance, and then the gamma and alpha are just the exponents. So we abstract the transmission rate matrix between 2 cities by this formula. Next, please. So we just used maximum likelihood. Because we know the time distribution of importation, so we can write down the likelihood function for these sequence of observations of the first cases. And here's our point estimate. The graph shows the probability of importation, time of importation for each city. Sorry, it's a probability density function for the time importation for each city. As you can see that it's roughly in the right order where Kelowna is the first imported city, so it has a larger probability than the Abbotsford and Prince George are the become the second and third cities. However, Victoria has this large probability. It's probably just because Victoria has a large population. But one problem that we see from this figure is that the probability distributions can be approximated by an exponential distribution, which means that the highest importation rate is at the beginning, which seems to be not quite realistic, and not surprisingly that because our model is too simple and we have to consider a few other factors. Next, please. Yes, so one thing is that when a city has a case, it doesn't immediately export cases, right? The case has to grow in the city. So there has to be a delay from observing the case to exporting the case. And similarly, when a city has a case, we don't immediately observe it. So there's a delay from having a case to we observe the first case. So with that in mind, how can we incorporate these delays? The simplest idea that we thought about is, well, we just think that before the city can transmit to other city, it has to go through another state, and that state can just be an extra node on our city graph. So that Vancouver has to transmit to export to Vancouver exporting before it can go to the cases can go to other cities. And similarly, Vancouver has to go to the Vancouver observed in order for us to observe the cases. So then each city becomes 3 nodes, and the exporting nodes would connect to other cities. And the observed nodes are what we can observe in the data. So now the 5 observed the nodes are they're observable. They're linked to data. All the other nodes on this graph are hidden nodes. They're hidden variables. We can't observe them. But then you can see that the graph becomes more complicated, and the transmission rate from nodes to nodes becomes more complicated. Especially, we can't really estimate the 5 delays from importation to exporting and the 5 delays from importation to observation. Then we have 10 more variables, but we only have 5 data points. So there's no way we can directly estimate it. But luckily, these 2 delays that we need to add in, they're all related to exponential growth. Now, the exponential growth, it could be related, it could be influenced by control measures, or could not, maybe not. For example, the first case in February in Vancouver, there was no control measure implemented in BC, so the growth would be exponentially growing. But for example, if we're considering importation from China or other regions in the world, there the control measures has been implemented. So the exportation rate would not be the growth without control. Next, please. So we really need to understand whether we can estimate the growth rate with or without control. For that, we have 2 sub-projects related to this. One is to understand whether we can estimate the effect of age-specific control measures like school closures or workplace close downs, etc. And we have looked at the 3 Canadian cities, Vancouver, Greater Toronto area, and Calgary. You can see that these are the case and adult case. The adult cases are red, and kids and youth, that's 0 to 19-year-olds, are blue. And you can see that they are roughly in parallel for the whole year of 2020 into early 2021, and that's not surprising because really these cases, this figure shows that the epidemic is pretty much in the exponential growth stage. That's why the 2 curves are pretty much parallel. And the colors in these figures tell us the specific age-specific control measures. When red means the control measures strengthened, when green means relaxation. So as you can see, pretty much when there is a green period, the growth rate starts to increase. And when the control measures are strengthened, the growth rate starts to decrease. Next, please. So we fit a 2 age group as EIR model to the data, and this work is done by then master student Tanya Phillipson, and she's currently a PhD student here. we looked at the periods where no control measures was implemented, and we use it as the baseline measure to a baseline period to estimate the transmission rate. And then for the other periods, we mostly just estimate the effect of control measures. That's how the sigma epsilon I terms. That's the reduction in the transmission rate. Next, please. So as you can see that we can estimate the age-specific effect of control measures on the R0. And you can see that when there's a green period, the epsilon, the reduction in the control measure starts to become larger. So there was almost no reduction in green, sorry, the epsilon is larger means the reduction is small. When the epsilon is close to 0, the reduction is really strong. So as you can see, we can fit that, and we can actually look at some of the interesting effects that I'm not going to talk about too much here because of time constraints, but we can look at the effect of holiday seasons like Christmas seasons, for example. We can look at what if the control measures were implemented differently. We had that done in our research. We just didn't show it here, but the key thing is we would be able to disentangle the effect of age-specific control measures and use that to understand the growth rates at different stages of the disease. Next, please. Another thing that we want to look at is contact tracing, which is an important control measure that has been implemented really early in almost everywhere in the epidemic. So there has been contact tracing models dating back to in the time of SARS in 2002, 2003 timeframe, and that those models basically assume a fraction of the cases were contact traced, which we don't think that's the case because the contact tracing is a dynamic process. We wouldn't be able to control exactly a fraction of the cases being contact traced. But how do we model it? We just look at the tree of transmission, and this is a quick illustration that if we have an index case, they spread in the population. With or without a contact network, it doesn't matter. But eventually, we do see these cases transmit to others, they transmit to others, and they form a tree of transmission. And on this tree of transmission, the control measures are put in, for example, the contact tracing are put in once a case is diagnosed, then they would trigger contact tracing, and the contact tracing would trace back to their infectors or their contacts. And so contact tracing is just a operation on this tree of transmission. And so we want to understand how we can model this process. Next, please. So this work is done by Manting et al. Manting Wang, she's a PhD student at UVic, and we had a simple toy model to understand SIR dynamics and control and contact tracing. And then has just finished a manuscript that we submitted out. It's under review. Then we looked at the SARS. We looked at the SEAIR with asymptomatic transmissions. And it's a pair approximation model. I don't want to go into too much details, but the contacts for transmission form a pair. And this contact tracing happens along these pairs. And these are the pair dynamics. Next, please. And if we fit our model to data, we can figure out if we fit it to the epidemic of Toronto in March and April 2020, where there are different periods where control measures were implemented. So this figure shows the result. The left column is the SEAIR model. The right column is SEIR model without considering asymptomatic transmissions. The first row is the RC control measures. As you can see, the red curve is the best approximation of the real data. So contact tracing reduces RC in a non-linear way, but it quickly approach saturation, and other control measures like contact, social distancing, workplace closed down, etc. There were implemented, and you can see there's an immediate decrease in RC caused by that factor. And then the contact tracing effect settled down, so the RC approaches a constant. Then another control measure strengthening was put in, so the RC was decreased. And then we looked at different possibilities. What if our contact tracing coverage probability, that means if some patient is identified, what's a probability that one of its contact would be identified? And if we can adjust that probability to see the effect. And when p equals 0, that means no contact tracing. And the second row of the figure of the panels, or the I of t, the prevalence.
Colin, you're a little bit over time. You're at 16 minutes right now. So
oh, I'm sorry. I lost track of time, but we're there. Next piece.
Okay.
Yeah. So.
I'm sorry.
Yeah. No,
there we go.
Thank you. So now we know that we can figure out the exponential growth rate with or without control measures. We can integrate these measures or the estimated growth rates into our model, and then we can use the expanded model to estimate the importation time distribution using our extended model, and that would be our next steps. Thank you.
Okay, thanks very much. The next speaker will be Fritjof Bucher from University of Ottawa.
Yes, hello. Can you hear me?
Yeah.
Excellent. Second question, can you see my mouse? I guess not.
No.
No, okay. That's a problem. Anyway, so yes, thank you all for being here. I want to thank in particular the steering committee for OMNI and Huaiping, of course, for steering this ship for the last 3 years. It's an enormous amount of work, and I'm very grateful for them doing that. I also want to acknowledge that the work that I'm presenting is actually mostly done by Francisca Olayide, but unfortunately she had a health emergency, and she was planning to be in Toronto, but she can't be, and so I'm jumping in here from far away. I hope that I will do justice to what she has done, but if not, then it's not her fault, it's mine. Next slide, please. So I don't need to say much about this. We all in this room know that infectious diseases are a big challenge for public health. And in this project, we're thinking about this as a critical transition. Let's say a virus gets more virulent over time, or as winter approaches, we all spend more time indoors, and so transmission can increase. And what we're looking for is early warning signals. We have heard about this before, and I think our approach is somewhat different from what we've heard before. And so we'll see what kind of the connections are. Next slide, please. So our questions are, what kind of early warning signals can we get based on the mechanism of the disease that we put in, let's say, an SIR model? And which variables give us the best, in some sense, of these early warning signals? And then also something that we've heard before, to what extent can a media compartment help be an early warning signal? Next slide, please. So we chose, for starters, we chose an absolute minimal model where we said we have susceptibles. We have two kinds of infected people, the ones with weak symptoms who probably don't go to the doctor, so for whom we don't have public health record time series, and ones with strong symptoms who do go to the doctor, so we do have a public health record for those, and then a recovered class. And then in addition, we put this media compartment in that we called M, And so we're thinking about social media here where any one of the 4 compartments can post things, but they can also interact with posts that other people have put there. Our beta is the parameter that may vary linearly in time, or in general may vary in time. So that's the idea that the virus is evolving or things are changing. So we're getting indoors in the winter, so we have higher transmissions. Next, please. So we analyze this model in 2 different ways. One of them is when the beta is a constant. And then we can just go for the classical R0 computation. And there is a formula there that you don't need to worry about too much. But the point is we're going to compare things with respect to this R0 later. The second thing is then that we took a stochastic version of our model. So we included demographic stochasticity, ran our model and looked for various time series signals. Next, please. So here is a typical simulation that you see. On the x-axis, you have time. On the y-axis, let's say on the left plot, you have the infectious component, the infectious individuals. And you see 2 straight lines, the R0 equals 1 line, the blue line, and you see the change point line in red. So I'm going to explain those 2 a little bit more. So over time, our beta, our infectiousness, our transmissibility increases. And so at some point during our simulation, we'll get to the point where for that particular beta value, our R0 is equal to 1. So that's the blue line. And then we see the time series. It's of course, the black line there, the black wiggly line. And so we used some R package to calculate a change point from where this goes from pretty much 0 to an infectious disease outbreak. And so what we see is that typically this change point happens much later than the R0 equals 1. So by the time we see the outbreak, R0 is already much larger than 1. And we analyzed that, we saw this consistently for the different compartments. So here on the right-hand side in the top, we have the weakly infected, and in the bottom, we have the media compartment. And so rather than just looking at a single time series, we wanted to do some more analysis on these time series. And so we calculated the autocorrelation and variance, and we split things up into 2 segments. The first segment being the one up to the bifurcation point where the 0 state, the disease-free state becomes unstable. And then the second, okay. So yes, no, next slide is good. So what we found was that the autocorrelation and variance both exhibited a stronger response at a change point than at the bifurcation point. So they were both better at predicting the change point than showing the actual bifurcation points. And they were both delayed, as you saw. We also saw that variance typically was a better distinction in the segmented time series. And we saw that the signals from social media can be as accurate as those from the reported healthcare, so from the infectious individuals. Next. So this is kind of a proof of concept where we have this mix of a mechanistic ODE type model and then a time series analysis for early warning signals. And we want to do a sensitivity analysis to see how the early warning signals respond to the parameters on the model, but more importantly, also the structure of the model. So we want to try this with different structure, put an exposed class in and these kind of things, and see which kind of early warning signals we can expect and what kind of a delay we can expect and how useful these things are. We want to also include other forms of stochasticity. And I think I said already the last piece. And so then we can see which of the signals could be most useful in a public health setting. Next, please. And I think that's the last. Yeah, so there are a couple of references for the early warning signals that we used, which are probably more commonly known or have been developed more in the ecological literature, but are just as useful here. And next slide, I think, is the end. Thank you all for listening.
Great. Thank you for talk. We have a comment from Amy. Did you want to say something, Amy?
Oh, just to highlight also that Francisca made other contributions by authoring a report on the ARMS summer school, which has appeared in the CAMES newsletter as well as the Society for Math Biology newsletter. So just thanks to Francisca for doing that. It's a really well-written report.
That's
Thanks,
awesome.
Amy.
Any questions in the room here?
Just one question, you mentioned bifurcation point. So that bifurcation point, it is stochastic bifurcation, or this is the bifurcation point of the ODEs before?
Yes.
Stochastic?
Yeah, so we're doing two kind of different approaches here. One is we're thinking of beta as a parameter, just a parameter, and then we can calculate that bifurcation point analytically, like next generation method. And the other thing is we can take the beta and increase it linearly in time, and then we can plot the time series with respect to beta so that we have at every time point the beta that we see in the bifurcation diagram as well. So we can compare the two.
Thank you.
Other questions or comments? Okay, thanks very much. Okay, the next is a joint talk by Shan Gao and Anit Chakraborty, 14, and you can use the computer right here. Okay, and I will go over here. Sure. Okay.
Hello everyone, thank you so much for having me here. I am Shan Gao, a PhD student from the University of Alberta. Today, Ahmed and I will talk about our current progress on Scene 3, segment 1. So this is the acknowledgement. We have 5 professors and 3 HQPs involved in this work. And also I would like to extend my sincere thanks to the ILMDE lab members and the Lewis Research Group members for their insightful suggestions and feedbacks. So the background. The prevalence and the recurrence of infectious disease occur very frequently around the world, and some of the infectious disease are mild in terms of the symptoms, and they can disappear very quickly without attracting much attention, while some can be more severe and long-lasting, for example, the COVID-19, right? So therefore, the balance between the risks associated with the infectious disease and the costs of the preventative policies as well as their consequences has been a prolonged challenge. People are expecting to implement the optimal measures. But the essential problem in infectious disease prevention and control is the timing of the interventions and the predictability of the disease outbreaks. So in our work today, we conduct the binary classification of 2 types of bifurcations. The first one, the transcriptional bifurcation, corresponding to the disease outbreaks, and alternatively, the null bifurcation, indicating the normality. So far, we got 3 papers in the draft form for 3 different programs or projects. And next, we will explain them briefly. So yeah, Amit, you can introduce your first project.
Thanks, Shan, for giving me the floor. Hi, everyone. My name is Amit Chakraborty, and I'm one of the HQP working in this project. I was involved with project 1. So we are talking about the early warning signal of infectious diseases. And as you know, like the early warning signals are very diverse and can be generated from different types of data. We have seen many presentations on them. Like it can be generated from wastewater-based surveillance and the Twitter data and the hospital bed management, etc. But here in our work, our early warning signal is based on the number of reported cases. So we generated we work on generating early warning signals based on number of reported cases. And as you know, like the infectious disease data are often convoluted with different types of noises. So we consider the white noise, multiplicative noise, and demographic noise. So there are some already called generic early warning indicators for early warning signals, such as variance and lag 1 autocorrelations, which are very widely used. but the performance of these generic early warning indicators varied with the different types of noises that's involved in the data. And here, our focus is to use a deep learning model to generate the early warning signal. And as you know, like if we can properly train the deep learning model, then it can outperform like any generic early warning indicators. Okay, but to work with the deep learning model, you need a lot of data to train it properly. And fortunately, we have a previous deep learning model, which was developed in the University of Waterloo, led by Professor Chris Balch and his team. So that deep learning model was developed to capture the tipping points in the ecological models. But the simulations that was generated in that deep learning model was based on random dynamical system having polynomial terms, and only the additive white noise was considered in there. But as you know, like the infectious disease have different types of noise involved with it. And when a new disease is coming, so we really don't know the mechanism of it. So we started with very basic model, which is a SIR model, and we considered three different types of noise, as you can see here. So we use these three different models to generate the training data for the deep learning model. Okay, so we generated 100,000 training data for the deep learning model, and the training data have two types of classifications, as shown in the earlier slides. So we have one scenario where you have the transcritical bifurcation simulations, but the bifurcations is occurring like anytime randomly between 0 to 1500. And we have another classification, which is null bifurcation, where you don't see any bifurcation between a time frame. And for the transcritical bifurcations, we took the pre-transition, like the pre-transition data, the data before the transition happening. And we took all the 100,000 time series to train the deep learning model, which we refer it as a SIDATR model. And the PODATR model is the pre-trained model, which was developed by Chris Balch and his team. And we have two other early warning indicators as well, like variance and lag 1 autocorrelations. As I mentioned, those are generic early warning indicators. So we trained the model, and we tested on different simulated model as well as the COVID-19 data of Edmonton. And you can see the generic early warning indicators in here, like variance and lag 1 autocorrelations, their performance, and we evaluated the performance based on the area under the ROC curve. Their performance is varied with different types of noise, like variance in outperform in some of them, noise-induced model, and lag 1 autocorrelation is outperformed in some others. But in our model, like the first one is SIDATR 500, which was trained on 500 data points, and another one is 100 data points. So in these two models, you see like the performance has improved, and it outperforms other models, like in all the simulated models as well as the COVID-19 data. So you can see like since the generic early warning indicators performance vary with different type of noises, also the machine learning models are sensitive with the different lengths of training. So we also investigated these scenarios, and Shan is going to present in his next slides. Thanks.
Thanks, Ahmed. So let's move on to the project 2. So this is the illustration for the project 2, the detection of outbreaks using the time feature-based time series classification for the risk misjudgment reduction. So as you can see on the upper left corner, we simulated 3 data sets following the same process as I just explained. They are the white noise data, environmental noise data, and the demographic noise data. And additionally, we have the 4th data set called the mixed noise data, which comprises the other 3 data sets. And then we slice the original time series because, well, at least for the transcritical bifurcation data, we cannot use the data after the transition point because we are expecting to make the early detection of the potential outbreaks. And then we computed 22 statistical features and alternatively 5 early warning signal indicators. Actually note that these features are numeric data, and there's no overlapping between these 2 groups. And finally, we partition the data into the training set and the testing set. So this is the pre-processing for the data we have. And I think the title is kind of self-explanatory because instead of using the time series directly, we extract the features from the raw time series and then we reduce the dimensionality of the data and conduct the classification tasks. And here, as you can see in the green box, we have so far for datasets, 2 options for the feature extraction. And we also use 4 predictive models, as you can see in the green box as well. So as a result, we got 32 classifiers based on every unique combination of these options. And then we documented the classification performance on the withheld testing set. But this is not enough. So we further changed the time series lengths, and we also changed the gap between the last point of the time series and the transition time point to see the relationship between the earliness and the accuracy. Because ideally, we expect to make the detection or prediction as early as possible while maintaining a certain level of the accuracy. And finally, we use 3 different real-world data sets to test the performance on these 32 classifiers, as you can see here. Let's take a look at the results. So the first result is we observed that the features we just mentioned are computed from 2 categories, which are the transferable the pre-translation data and the new non-application data. They are significantly different based on the result of Whitney U test. And also for all these 32 classifiers, they showed near perfect performance on the withheld testing data set, which gives us the hope to proceed. And also, we see that all the classifiers following the framework can handle the cases that are far from the transition points. And also they can handle the cases that with different time lengths. And finally, I want to mention that for these classifiers we trained, they exhibit inconsistent performance on the 3 empirical data sets I just presented in the previous slide. However, there's one classifier that exhibited the consistent good performance on these 3 empirical data sets, which is a good thing. Finally, let's talk about the project 3, which is mainly contributed by Reza Mari from Brock University. Unfortunately, he's not here with us today, so I'm trying my best to deliver the key message he sent to me. So previously, Barry et al. Proposed the deep learning model with the long short-term memory network and convolutional neural network. And also they simulated the data, the training data based on the 2-dimensional dynamical model with the random polynomial terms. So these are the architecture and the training data sets for the Barry et al.'s work. And also in project 1, we borrow the same network, which means we use the same architecture and the same hyperparameters. But we use some more context-specific data, which is the noise-induced SR model simulated data. However, in project 3, we changed the architecture. So the architecture still contains both LSTM and CNN layers, but they are implemented in parallel. And also, we use these 2 datasets as we just described here, just now. So these are the key results for them. So this is the diagram, the histogram for the accuracy of 3 models, 2 for the previous work and our work. And this one, our model here, refers to the project 3 final model. And we can observe clearly that for our model here, this outperformances the other 2, which is a good thing for us. So I think this is pretty much everything I want to share today. Thank you so much. Thanks.
All right, our last speaker is Manas Papagelis.
Thank you. Hello, everyone. Our topic is mobility-based models for epidemic spreading. And I'm Manos Papagelis. I'm the PI of the project. So basically, okay, mention some. So what we're trying to do in this project is that we try to take the mobility as a mechanism of infectious disease spreading. And as we know, as we move around, come closer to each other, and then the epidemic can spread, and then you take it with you, and then after some days, it moves on to someone else. So there are a few research objectives in this project. First of all, we would like to develop some mobility-based models, spatiotemporal, right, for epidemic spreading. We would like to incorporate mobility-related heterogeneity and risk in epidemic modeling. So this means how, what if someone moves a lot, right, based on the job that they are doing or the habits that they have compared to someone that is not really moving and is working in a basement alone, okay? And then based on this, we try to design some targeted mobility-related interventions. The keyword here is the targeted, right? We want to compare this to a null model. What if everybody moves the way they do? And what if we remove 10% of the people, let's say as an example, based on information that we have about the mobility patterns, as opposed to randomly removing 10% of the people, okay, which will be the null model. And then all this is just to, at the end, have some conclusions, right? Can you have some data-driven decision-making to inform health policy? And I'm not going to give you one single problem and one single solution to this, because there are a number of papers and work. So I would like to encourage you to read some of them if you are interested. But the main research outcome is that, of course, we had the chance to train many very smart and hardworking HQP, right? There were 2 students directly involved in this project, and a master's student that now transitioned to a PhD, and a senior undergraduate that also transitioned to a master's. But there were also a few more graduate students from our lab that were involved partially in this project, and they were here. Okay. And then in terms of papers and publications, we had a journal article published in Big Data Research, and 2 conference papers in MDM 2022 and the 6 Special 2023. These are all conferences related to mobility, okay, and good reputable conferences in data mining and computer science in general. We also had 2 also papers in the 6 Special EPI, a specific workshop about epidemic and special transition. And also we have some open source synthetic mobility data for others to use, and also the data generator in case you have your own mobility data and you want to transition to, I'm going to spend a few seconds referring to that. Okay, so if you have to see each of these works separately, the high level idea again, I'm not going to give you details. In the first one, the topic was the more general epidemic spreading trajectory networks, okay? And what we try to do here is the following, right? The only assumption that we have is that we have historical data of individual trips. So let's say we know how everybody moved. These are enabled by technologies that we are already there, right? So whenever you have your cell phone, any GPS-enabled device, basically, plus some other ways to do it, but let's focus on the cell phones, you can have the transition, the trajectory history. And then based on that, what we want to do is we want to assess what is the relative risk of the infection for individuals, right? How we compare different people based on different patterns. And then based on this, we want to assess the size of the disease outbreaks that can be due to specific individuals. All this idea of super spreaders or non-super spreaders, does it really hold? Like, can we evaluate these things? And then based on these simulations, okay, we try to see what are some good strategies to have impact of non-pharmaceutical interventions. Okay, so we're not doing any pharmaceutical intervention here. Their main idea is, can I ask people to behave in a different way in terms of mobility in order to have some impact to the whole intervention, to the whole epidemic spreading. So here is the idea. Sorry, the animations are not there, okay, because I'm using a different laptop. But if we take it from the left up, following, the main idea is that we start with trajectories, and this demonstrates how things move around, okay, how everybody's moving around. But then eventually we can turn this to a mobility network. Okay, so basically, whenever you're in close distance with someone, we can assume that 2 nodes can be connected with an edge. And as we keep on moving around, these edges don't exist anymore, right? They're dissolved. So basically, based on this, we can build first, based on many different ideas, what is the infection risk of these individuals, okay? And these are mostly graph theoretic approaches to determine what is the importance of every node, but you have to take into consideration the epidemics, right? So for example, how close you are with each other, or for how long you are close to each other, but then you have to also normalize this. Like it doesn't make any difference if you are 1 hour or if you are 2 days together, okay? So there are a few ideas that we're exploring there. And then based on this, we also developed some stochastic epidemic modeling, agent-based stochastic epidemic modeling. So what is this basically doing is that every time that we know that someone is infected, if he's in close proximity to someone, which means connected, what is the chances of this propagating to someone else, right? And then we take this to the whole network. So this describes a dynamic network. You cannot really see it, but it's a spatiotemporal dynamic network. It's not a static network, right? So everything moving and changing. And then based on that, we have some targeted intervention policies. And at the end, we have a very elaborated evaluation metric for different aspects where we describe many different things, okay? Okay, so this is the main work, but then we take this work and we move to microscopic modeling of spatiotemporal epidemic dynamics. One thing to recall from the first slide is that we use the spatial network, right, to see who is connected with who, but we're not using your place, right, because of privacy concerns. So basically all this is translated to a temporal network. But in this work, in the next one, the diaphragmic work, we actually use the space, right? To say, how about if people don't care about the privacy concern there, and we know where they are and when this happens, okay? So based on these ideas, again, from the top left, we start with all the trajectories. You cannot see the dimensions again. But now what we do is we tessellate the whole map, right? The whole space in hexagons. This is a general practice in that domain. And what we do is we do microscopic modeling, like where everybody is located at what hexagon. And based on this and some hierarchical modeling that we have, like we can do the same thing for IKEA, right? Or something that is very large. We can develop, again, models, spatiotemporal models of epidemic spreading based on which hexagons we're occupying together, right? And these hexagons are defined in such size to allow epidemic to spread, right? They are not kilometers away. But now that we have this information, we can come up with very interesting things. For example, we can develop down left risk maps, right? So if you have the whole Toronto, and if you have millions of trajectories, historical trajectories of people, you can easily determine which areas are more risky than others, right? And here the relative risk is the importance, okay? So the heat map is just giving us this. And if we have this, we can also do many more interesting things. For example, we can determine what is the risk of taking a specific trip, right? And here we're assuming pedestrian, like imagine that you take York University as a place, so everybody can move around, you can move through buildings, you can move outside. So if you want to go from here to your place, which path is more risky based on trajectory history? Okay, and based on this, we can build also some specific applications, right? So if I want to go there, what will be the most less risky path to take? Okay, so basically we took this last idea and also had a demo. Okay, we call it a mobility-based recommendation system for mitigating the risk of infection during epidemics. The main idea is that you can submit where you are going, okay, and then since you have done all this background analysis based on historical data, we can provide what are some alternative paths and what is the risk for each of the alternative paths. Okay, so you cannot see the details here, but this is if you go to a specific location. Another query that you can do is that you are interested for specific points of interest. Right? So let's say you want to do grocery shopping. So you're the red dot there in the middle. You say, I want to do grocery, let's say within a range. These are the options that you have. So how each of them are associated with risk, okay, based on historical trajectories. So that's good, but one problem of this is that if everybody queries at the same time, for everybody, the safe place is the same, right? So we want to take into account this in the next work. Let me skip that slide. Okay. This actually, I don't know what is this. Okay, my language, okay, that's fine.
I cancel that.
Sorry.
Not from your side.
Sorry?
Not from your computer.
Oh, it's not mine. Oh. That later.
Again, here, high-level methodology, the idea is the same, right? That you have an origin, you have some destination, there are alternative paths, I have tessellated the map. So now every trajectory is going through specific hexagons. And then for each of the paths, I can aggregate the risk and I can say this is more risky than the other. Okay. So what I was trying to say is that this is happening using historical data. But what we try to do in the next work, which is also published, is that we try to do an online recommendation, right? So what if everybody, like, let's assume that you have concurrent queries, right? So everybody's querying, by everybody meaning Toronto, you can have thousands of queries coming within a minute, right? Where supermarket should I go to do my grocery? So what we try to do is we try to evaluate different strategies, right? Here, I'm not going to give you all the details, but these two people, they query at the same time. So there are many different strategies. You can go randomly to a place, or you can go to the one that is closest to you, or you can go to the safest based on historical data, or you can go to the safest based on historical data plus online information of how other people are going to go. Because you don't want to recommend one specific place to everybody, because then there is change also. Okay? So this is what we try to do in this work. And at the end, I discussed about online data sets that we provide, okay? And we call this point effects. It's a general method. It's not only for epidemics. So if anybody works with mobility trajectories, etc., and you want from points that describe trajectories or from points of interest, you want to go to sequence of hexagons, this is a tool that you can use. So the main idea is that first we tessellate the map in many different resolutions, like how big are these hexagons. So it can be low resolution or very high resolution. Here is Manhattan, New York, okay? And then what we do is we treat trajectories as sequence of hexagons, okay? There are many good properties for this. Like, first of all, we reduce sparsity. And second, we can use this input to very popular machine learning sequence models, okay? So you can do predictions, you can do other things, not directly related to epidemic, but can be related to that as well. So basically, instead of having a language, here our language is the trajectory, right? You have sequence of hexagons coming from a predefined language, which is the number of hexagons that you have. Okay, so I'm just describing here the process, how we do that. I don't have to cover it in detail. And just to finish, these are the data sets. They're available online at Zenodo. It's a popular repository for research data. And also the data generator, the GitHub is available there. Okay, you can take a photo, or you can ask me later, have my time. So to conclude, what we try to do is we try to work with mobility-based models, and the main conclusion that it really can help in many different ways, okay? Because it can help us to understand transmission dynamics in this spatiotemporal dynamic network. Of course, do many different types of prediction modeling, and then we can identify high-risk areas, okay? We can optimize the intervention strategies, like instead of asking everybody to stay at home, can I ask 10% of people, but specific ones, to stay at home and have what impact that will have, right? Maybe we can reduce the epidemic. And of course, there are some concerns. Okay, we should not forget about that. Some privacy consideration and ethical consideration. So the idea is, can we balance the use of mobility data with privacy and ethical considerations? Okay, and this is an open question, so don't have the answer. But I think it's there, right? So these are the publications. Again, you can have a look, or you can search my website. These are already published right now. Okay, so everything is available. The models are available. We usually provide GitHub for the code and for the datasets, but datasets can be general also for other programs. And of course, credits to all my students, right? Some PhDs, some masters, some graduate students already. That's it. Thank you.
Yeah, I have a question. So that's very impressive the way you're doing it, but I also worry about the possibility that it could lead to marginalization of certain neighborhoods. Maybe we don't go to that grocery store because of socioeconomic conditions, right? That the algorithm would come up with. And how do you, like, I know you bring up ethical considerations, but how do you actually deal with those in reality?
Yeah, this is a very good question, right? And these are all concerns that probably were not the right people to answer from a very technical perspective. There are other people that are more experts on how to do it, how to execute it, how to implement it. But we have some very interesting data sets some very interesting results in our analysis, right? When we talk about super spreaders and non-super spreaders, that show that eventually it doesn't make a huge difference in the spreading, right? So you might be a super spreader and you can spread the epidemic because of the job that you are doing, okay, not or where you are working, okay, if you want in terms of location. But it might be the other way around, right? It might be someone that is not considered a super spreader based on mobility, but he gets in close contact with someone that is super spreader and then it goes a cascade. So then who are you to blame, right? But at the end, if you want to control the epidemic, I don't know how much we should care about this or how to eventually solve it, right? So if it's happening in specific areas, and if we have to get some measures there, let's do it there, right? Yes.
Related question. So I imagine when you're running these risk trajectories, it's in the context of a simulation where you actually have transmission happening within your network. Have you compared that to a situation where all you're using for risk information is the contact frequency? So essentially, assuming in a situation where you had very little information about the spatial location and you know, no way to inform people about exactly where things are happening, do you still get comparable information about risk just by identifying trajectories with higher contact than lower?
There are a few points that you mentioned, right? So one thing is how good are the simulations, right? At the end, like, and we tried our best. Simulations are just simulations, so we tried our best to differentiate between people, different activities, different areas, and so on. But some part of the work, like the later work, is also using real data about visits and points of interest. So that's something that we demonstrate that if people were aware of the recommendation, and then we take into account, of course, how much you follow the recommendation, okay? How many people will follow the recommendation? That's another critical point which we explore. So the data is there, right? Now, coming to your point that is this what exactly is going to happen? You don't know that this is exactly what is going to happen. Right? These are all working in expectation, like it's a stochastic model. But going from the aggregated data that we're using now, that we just know how many cases we have and nothing else, like this can give you much more information. Like this is the main premise of this approach. Like you can do quarantine in specific areas. These are things that people are doing, right? You're closing whole neighborhoods in different countries, maybe, but you're doing, if we don't move, my understanding is that the epidemic doesn't spread, right? So eventually dies off. So if we can do this in a controlled way, not to avoid moving at all, like stay at home always and nothing else, but having some targeted intervention, which means that with smaller intervention than what we're doing, you can have the impact that you have, so you can have the hospitals keep on working, you can have doctors keep up with this. I think this is the premise. And the technologies are there, right? We just have, and also I have an argument about the privacy issues, right? So if we already reveal all our privacy to so many companies, private companies, about where you are, what you are doing, and we're doing this, why? To get better advertisement, right? To get more targeted advertisement sold to you. Then maybe we're willing to sell this for health issues. But again, this is a debate, right? It's not, there are many things you have to consider. Who's keeping information for how long? Can we make it in an encoded way? So you don't really care who is the actual person, but.
Thanks to all the speakers from CP3.
Is there a question about this? Or maybe I'll take it.
Maybe take it later. Yeah. And I think what we're going to do is hand it back to White for a roundtable discussion. Thank you for the presentation.
There's three items before the discussion. I'd like to mention, because we are getting close to the budget end year, it's like the older networks, so which will be March 31st this year. You didn't see our program manager Natasha, because like she recently does not feel well. Otherwise, she will be here presenting some information about the budget closing Form 300 and summary. Just the microphone. Yeah, the summary to close our SIM 1 to 4 activities and the budget. Of course, I mentioned for SIM 5, we are still working on that. Of course, we will connect to the whole network to make a move in order to make a success. So that is one. For the discussion, there are two parts I'd like to mention. One is for the whole network, our purpose is to develop the early warning capacity for emerging infectious diseases using One Health approach. So this is our objective of the whole network. So there are two parts. One is how to build this early warning capacity, because we already see so many people are working individually or by group, developing such early warning capacity or system. How we are going to build to represent the OMNI early warning capacity and the data portal. This is one. The other thing is about the sustainability. So we're getting approach to the end of this network. So we want a discussion. So after the discussion, we will bring back this to the co-directors and board of directors. We will have a discussion and then get back to the whole network. Now, in fact, well, they can have your opinion about the data portal sustainability.
You want to make that a question?
So this is just the free
discussion.
Free discussion.
And it's about sustainability, data portal ideas.
Yeah, ideas. Yeah. Anything you think is important. So we just, yeah. But
I have a question for yourself, my opinion, Mark, and others, and that is, what part of sustainability in the future, can you give us any update on the broader EIDM consortium and kind of a path forward linking us to the other EIDM networks?
A few times I mentioned this about the pan-network discussion, because we have 5 EIDMs. So starting of last August or September, so suppose we did the last one. So I keep sending emails to the brother networks. We need to continue the conversation. But unfortunately, the meeting and of the consortium PIs co-lead the meeting hasn't really happened since last August. It's important. We will keep pushing. The pan network supposed to come to discuss. One other thing, Mark participated one of the roundtable discussion organized by NSEC. So we participated. They collected the opinion from us. We haven't heard any feedback from them yet. The other thing is, like Mark has been leading, you see the presentation of the white paper. So that's outlined the future vision. So that is something will serve as a kind of guideline, for the future development. Other than that, for the pan network discussion, nothing more to report.
Like to add a little bit, like the way the EIDM funding went was, it was very good to get funding, but it would artificially broke up the Canadian modeling community into these different groups. And so when you do that, there's 2 risks. One is overlap. So maybe you're funding the same person to do the same thing for different groups. And the other is some sense of competition because they're competing for funds. And that's not really, those can be negative, right? And so it's my conception, and I believe the conception of the people that attended this panel meeting and wrote a white paper was that we need to find ways to unite the Canadian modeling community in the future to build capacity, not in this sort of fragmented way, but in a more coordinated way, in as much as people want to do. Right? I mean, you can't make people do things they don't want to do, but I think there is a sense of will to do that. But unfortunately, the federal funding mechanisms appear to want to break things up into pieces. And so one possibility is to try to have a sort of a group that go to the government and just say, this is what we want to do. This is why you need it. Find us some money. At a very high level and not waiting for funding competition. The other is like Jane and others and have applied to these by manufacturing networks. And again, they've been regionalized through the federal decisions about how to do that. But do you want to add to that, Jane?
Sure. So there is a Canadian Biomanufacturing Research. It was the F stand for. I can't remember. CBRF. Yeah. And so through this funding initiative, there are 5 hubs. And one, so there's like one in Ontario, one in Quebec, or 2 in Ontario, one in Alberta, and one in BC. And Carolyn Tulane, who's at SFU, and I OPI with a bunch of people from the EIN, a proposal for mathematical modeling and statistical modeling and economic modeling to support biomanufacturing and pandemic preparedness. So the hubs are for biomanufacturing for pharmaceuticals and vaccines and for pandemic preparedness. So it involves some people from the EINs, but it essentially is trying to help move towards what we put in the white paper, to have a large Canadian network of statisticians and modelers and people in economics to work together to link people in the network to people into public health, to federal, provincial, regional governments, as well as drug companies, pharmaceutical industry, and so on. And so there's been interest already from different government agencies as well as pharmaceutical companies. So people are already contacting us to see how they can get connected to different people. And we just hope that in March, we'll find out if this network is funded, and that gives us a stepping stone towards what we really want is some sustainable funding for modeling networks.
Yeah, just to add to that, in fact, while so that is one proposal from the networks. In fact, the MFTH from First Institute, part of the OMNI, also put forward something that by Kumar and me, but we haven't heard anything. That is, basically follow the same line. The whole network seems like grouped into two proposals. One is led by Caroline and Jane. The other is from MFTH and part of OMNI, but we haven't heard about it.
There's a third one from
Master,
yeah.
that's on.
I guess just to contextualize my question from earlier, to what extent does the sustainability and future of the group in this room pass by the identity of OMNI versus something broader, right? And it sounds like there are these other projects that are going to hopefully bring people across networks, but the flip side of that question is, the specificity of OMNI is really the One Health modeling aspect. And in some of these new initiatives, are we able to maintain that? I think that was really one of the strength and unique features of this. And so in these, is that One Health component something that we're seeing being maintained and will be perpetuated, or is that something that needs a dedicated structure to sort of, we have a lab here, what's the pros and cons versus maintaining this artificial separation, as you said, of these different networks with each their own specificity versus coming together, and then what do we lose in that process?
Well, One Health is in the hub proposals. Is what it's actually.
Also, the pandemic preparedness, one of this.
I think our OMNI-RÉUNIS network is quite unique among the five networks. Of course, the discussion about the sustainability is the key. In fact, we want to see, especially we want to hear from the members, find out the ideas how we can really sustain this, because we spend a lot of energy get together to formulate this unique network. Just for the network itself, how we can find a way to make it, how to make it sustainable in what format in the next few years. As you see one thing which is very important, because this is the One Health network. The Indigenous 5, in fact, due to the challenges, but it gave us, very special position. So this, if we request the extension, so physically, this Omni network is extended one more year by extension. So this is due to the, Indigenous SIM, because that will be independently at the SIM. We request the extension from NSEC. So this, hopefully, this will open a door to the future, allow us to develop further, find a way to sustain the network. At the same time, I see, for example, maybe Elaine can say more, because there's the other global One Health network of Canada, which is led by Elaine. So the funding finished, but how we are going to still sustain, people get together, we are still able to do things. We have the super spread event. One possibility is I discussed with them, they are waiting to, for example, continue the super spread one. So that is endo the CDM and Omni network to continue to run certain activities to maintain, in some way, certain things about the network. That is just part only the few small things. In fact, this is the key. The discussion how we are able to, in what formats we are able to sustain this. This is extremely important. Across the network. In fact, the presentations has been really covered a lot, very informative and productive, especially encouraging in a sense. We have achieved a lot through the presentations. Of course, the discussion is not end, but we will continue to discuss and find a way to sustain in a format of this network. As you can see, this lab just opened because we had this opening ceremony. Definitely at York, because like the Omni was hosted by CDM at York. So the CDM will make the effort, especially here we have other members at York, try to maintain this network, make it, even though it is just started, I hope this would become a home of One Health modeling for the network people. Welcome anytime, come back to visit us and the lab. Anything else? Do you have anything to add?
Sure, yeah. I would like to say thanks to John for coming from so far and for providing a lot of inspiration for us. And so it's. I'd also like to thank Wai and Shizuka and the local organization team here. I know it's been a lot of work and it's done really nicely. So thank you for that.
Elaine, do you have anything to add?
Well, as Mark, I think these are the people I want to thank, and I'm sorry I couldn't be there. You probably saw why. So thank you, and thank you, Wai-Ping, for keeping all of this energy to keep the network working and running. You've done a great job, and I think we should all give you a hand, because I think that's been difficult.
Okay, I hope everybody have a pleasant and safe trip back. So we'll hear from us soon about next steps. Thank you. Now, next we move to the lounge at the Shirley Hotel. Okay.
So there is a lunch, is there?
Yeah, lunch. We have lunch is prepared like yesterday.